Hi, everyone. Thank you so much for joining us today. We have a great lineup of speakers. So we're going to get started with Robbie Pickering. Robbie is the environmental engineer with more than 10 years of experience promoting water efficiency and sustainable facilities management. For WaterSense, he supports the product specification development process and has helped develop technical materials to assist the commercial and institutional sector in implementing water-saving best management practices. We also are excited to have BK Ning from Innovative Polymers Incorporated today, and he's going to go over an exciting new proprietary technology for cooling towers. So I'm going to pass things over to Robbie.
Thank you, Tara, and thank you everyone for joining us today to learn more about WaterSense and also just water-saving opportunities within mechanical systems. First, I just want to welcome everyone today. This is part of a monthly series that Energy Star and WaterSense have that addresses water efficiency within commercial and institutional facilities. In the remainder of 2021, we have 3 additional webinars after this one, so certainly we encourage you to tune in if you're trying to learn more about understanding or reducing water use within commercial buildings. We have a lot to go through today, so I'm just going to kind of dive in and then hand it over to a case study today being put on by Innovative Polymers. So here we go. So first, a little introduction to WaterSense. The WaterSense program was launched by EPA in 2006 to help promote water efficiency and encourage innovation within manufacturing. We help organizations and consumers save water for future generations. The WaterSense label, which is displayed here on the slide, provides a simple ways for both consumers and businesses to really identify water-efficient products, homes, and programs that can help kind of reduce resource consumption. The label helps consumers and businesses identify products that have been independently certified for both water efficiency and performance. That performance element is something that kind of gets forgotten sometimes, but is a very critical part of our label. And in general, the label is reserved for products that are able to reduce water use by at least 20% and perform as well or better than their standard models. So there are a variety of residential and commercial products that are eligible for the WaterSense label that can be used in commercial facilities. The label is generally reserved for, as I mentioned, it's reserved for products that use at least 20% less water. But we have around 30,000 labeled models ranging from toilets and urinals to shower heads and faucets. And on the outdoor side, we label irrigation controllers and spray sprinkler bodies. Through 2020, WaterSense labeled products has helped consumers save more than 5 trillion gallons of water. That's a lot of water. And more than $100 billion in water and energy costs. So, the program clearly has had a pretty substantial impact. In addition to these product categories that WaterSense labeled, we also try to work closely with Energy Star to include water factors in some of their specifications. So, for example, clothes washers and dishwashers that are Energy Star certified are also water efficient. Within commercial buildings, water use varies depending on building type. So knowing exactly how your building uses water and where it consumes the most, either by tracking your meters and submeters or by conducting a more thorough water assessment and developing a water balance, understanding how water is used will help you identify potential efficiency projects and prioritize your efforts. This chart on the slide is an analysis that was done by WaterSense a number of years ago that shows that consistently water used for heating and cooling can account for up to 30% of a facility's overall water use. And even more, specifically in hot, arid regions where cooling towers and big mechanical systems are used, it can even be greater than 30%. So yeah, buildings with high process loads like hospitals and laboratories, data centers, they require a lot of cooling and oftentimes have high resulting water usage. So why might you be interested in saving water in your mechanical spaces rather than elsewhere? almost all mechanical or all commercial buildings use mechanical systems to provide heating and cooling, and in many cases, these systems do use water. First and foremost, important as all commercial buildings is the bottom line. So saving water can help reduce operating costs. Water and sewer costs consistently are rising higher than the consumer price index. I think since 2000, it increases about 6 to 8% per year. So, it's going up well higher than inflation. In addition, saving water and energy can help improve equipment efficiency, often reducing some maintenance costs or man hours that are required for repairs. Saving water can also save energy in a lot of cases. So, energy used to pump, treat, and heat water in your mechanical systems, reducing your heat load can also make your equipment more energy efficient, which then in turn also can save quite a bit of water as well. So this kind of water energy nexus is an important concept within mechanical systems in particular. And in general, just beyond the mechanical spaces in your building, finding ways to reduce hot water use, whether that be in a boiler or plumbing fixtures or commercial kitchens, those usually will have a commensurate water savings as well. And lastly, saving water in your mechanical rooms tends to be a little bit of a behind-the-scenes conservation effort. So sometimes facility managers or buildings may be a bit hesitant to implement efficiency in more, occupant-facing or visitor-facing areas like restrooms or landscapes, because there may be backlash or fear that there might be negative feedback from occupants or customers. Mechanical improvements kind of provide this behind-the-scenes opportunity for savings where occupants won't necessarily feel the impact of that. So we like to just say, just add water to energy programs. It's often not more difficult than that. It often just requires some focused attention from your facility management and facility staff. Most of you have likely been managing energy for many years now, whether through Energy Star or otherwise. So you likely have these protocols, procedures, and systems in place for helping to monitor and manage energy throughout your facility. And in many cases, adding water just requires the addition of specific water efficiency practices to your SOPs so that employees are aware of water use and can work towards managing energy and water together. Sometimes water management just requires you to pay a little extra attention to where water might be wasted rather than writing it off as something that is likely not very costly or insignificant. We suggest also adding water efficiency requirements into all your procedures or purchasing agreements as you might do for Energy Star. Often simple changes to your SOPs can reduce water without really incurring any renovation or retrofit costs. And sometimes for no cost at all. For example, facility managers should make all appliances and equipment, make sure these equipment are operated at their most efficient settings at which they can still operate effectively. Oftentimes some mechanical equipment can be you can dial up and down the amount of water going through it, to make sure it's being cooled an adequate amount rather than kind of going overboard. Also, small-scale retrofit or replacement projects for fixtures like shower heads and faucets can result in significant reductions with a pretty minimal capital expenditure. Lastly, continuous water use monitoring can help identify leaks and other operational malfunctions so that they can be corrected immediately. It also helps develop and evaluate a comprehensive project list of water savings opportunities. This will help you focus on water savings efforts as capital funds may become available, or if you have other renovations that are planned where water efficiency projects can be incorporated. Water meters are a vital tracking and measurement tool that can be used to track water use within a facility. You make sure that each source of water that's supplied by the utility is metered and tracked separately. So some utilities offer reclaimed water, for example. In some facilities, there's only one meter for the entire building called a master meter. So it can be very helpful to also install sub-meters on major water-using areas or systems such as tenant spaces, cooling towers, or irrigation systems. It's easier to spot areas to reduce water when you're accurately measuring and monitoring it. One thing I want to clarify is that adding submeters do not necessarily need a separate utility account. They are mostly used for facilities to manage their water use internally instead of waiting for a monthly bill or even a quarterly bill. This can cut response time for leaks or malfunctions significantly and save money. There are some flow monitoring devices that can be connected to the building automation system or otherwise connected to the web that can send alerts to let you know that a leak is detected. When identifying areas where water submeters should be installed, a good rule of thumb is to submeter any system with an anticipated water use greater than 1,000 gallons per day or 100,000 gallons per year. So large mechanical systems that use a lot of water, like cooling towers or steam boilers, are really great places to consider submetering to help track your consumption related to these specific systems. We also recommend submetering alternative water sources such as gray water or rainwater collected on site, so you know how much water you've collected and used, and how much domestic water you're really saving. And if you are doing metering and submetering, certainly want to put in a plug for Energy Star Portfolio Manager. This is a great place to track and monitor your water bills and meter readings. So as many of you are probably aware, Portfolio Manager allows building owners and managers the opportunity to track energy use, water use, and waste. We often like to call this the tracking trifecta. So tracking water use in Portfolio Manager can be done through the Water tab, which is shown with this red arrow. You can add your water meters like you do any other of your energy meters on site and begin entering data on a monthly or more frequent basis. Be careful to pay attention to the units that your bills or your meters are using. Those aren't always consistent. Sometimes it's listed in gallons or kilogallons or cubic feet or 100 cubic feet, so just make sure to pay attention to those units. Now I'm going to briefly pause for a poll question. So Rosemary's going to operate this poll. So is your organization currently tracking water in Portfolio Manager? Leave it open for a few more seconds.
Like about 45% or about 60% of people have responded, so let's try and make it an even 75%, then I can close the poll. All right, we can give it a couple more seconds and I'll close it. All right, so you have 15 more seconds and then we will look over the results. All right, so I have just shared the results with everyone, so you should be able to see them on the right-hand side of your screen.
All right. So I'm now going to walk through the major areas where mechanical water use kind of occurs within commercial buildings. Water is consumed in various mechanical systems used for heating and cooling. These systems include single-pass cooling, chilled water systems and cooling towers, and steam boilers. So we'll discuss each kind of best practices associated with each of these now. So single-pass cooling water, if present, has the potential to be the single greatest water waster in your facility. So when looking for opportunities to save water within mechanical systems, this is a really great place to start. Single-pass cooling is a situation where city water is plumbed to a piece of equipment to remove heat typically for a motor or a compressor. After use, the water goes right down the drain. So in commercial facilities, you might find this associated with AC units, walk-in freezer or refrigerator, ice machines, vacuum pumps, kind of, mechanical equipment or laboratory equipment. In any of these cases, the cooling method can use up to 40 times more water than is used to remove the same heat load that a cooling tower uses. So you can see how much water these things can consume. If possible, it is best practice to just eliminate these instances altogether. You can do this by either replacing water-cooled equipment with air-cooled equipment or providing cooling water from an existing chilled water loop. There are typically significant cost and water savings available from these changes. In cases where you can't eliminate single-pass use, make sure you're using the absolute minimum quantity needed to provide the cooling. Check the equipment specifications and make sure you're getting the maximum temperature rise in the water you are applying. Also make sure the water turns off when the motor or compressor is not running. Often water can flow and it's controlled by solenoid valves so that, when the motor or compressor isn't running, the water should shut off. But in a lot of cases, these solenoid valves can fail and the water will flow all the time. So this is a maintenance item that you should pay attention to and that should be addressed if you see it. In some cases, single-pass cooling water can be reused for other applications, but in general, it's just best to eliminate it altogether, which I'll illustrate a little bit on this next slide. So this photograph illustrates the potential magnitude of savings opportunity, particularly in setups where water flows continuously. On the left, we have a flow that's not much more than a trickle, about 1 gallon per minute, continuously flowing. That would consume 500,000 gallons of water per year and cost the facility nearly $7,000 in water and sewer costs. At the far right, you see the equivalent of a full flow garden hose. At 6 gallons per minute, you're wasting about 3 million or more than 3 million gallons of water per year, and that would cost your facility more than $40,000. So you can see the scale of how much water use and how much water costs you'd be paying to operate these single-pass systems. So fortunately, most facilities with substantial cooling loads use recirculated chilled water systems. These systems have several key components. There's a heat exchange unit that are supplied with chilled water that are providing space cooling or some other equipment cooling. This is where the heat load really comes from. Number two, there's a chiller unit that generates the chilled water through a refrigeration process. Typically, this chilled water loop is fully closed, so there should be very little water loss or consumption from the chilled water loop itself. It is good practice to have a makeup meter on the chilled water loop so you can see if there is any consumption or continuous makeup. That would be a good indication that you might have a leak in your chilled water loop. And lastly, the condenser on the refrigeration cycle may be either air-cooled or water-cooled. Larger units tend to be water-cooled using a cooling tower. We're going to talk in more detail about cooling towers now. So we have kind of everyone oriented to the discussion. I want to just take a moment to go over some of the basics of cooling tower operation. The concept is fairly simple. Water and air flow past each other, typically in a countercurrent or cross-flow configuration. In this schematic illustration, water is introduced at the top and flows down while air is drawn up through the tower by fan. As the air passes over the water, some of it is evaporated, which removes heat and reduces the temperature of the water in the tower. If you ever feel that chill when you kind of get out of the pool on a breezy day, even when it's hot out, that's evaporative cooling. And this is the principle that cooling towers use to remove heat. So there are some inputs and outputs from the tower that are of interest and will help with kind of the next few slides. First, there's the circulated cooling water or chilled water that is, or cooling water that is introduced into the tower to be cooled. This water is removing heat from a piece of equipment, in this case a chiller. Some of this water evaporates to remove heat. This is by design and is the purpose of the cooling tower. Some quantity is lost to small droplets called drift, although this is generally pretty small. Some water is then discharged as blowdown to keep minerals from building up in the recirculating cooling tower water. And lastly, makeup water is added to balance the losses that occur due to evaporation, drift, and blowdown. So we just talked about some of the water inputs and outputs from the tower, but what we're really interested in is where we can save water. So to save water, you can either reduce the evaporative heat load on the cooling tower, you can reduce drift loss, reduce system blowdown, minimize leaks or propensity for leaks. This is sometimes kind of just an unintentional form of blowdown. And then you can also provide makeup water from a source other than city water. So first I'll talk about reducing evaporative heat load. Evaporation is really the primary function of the cooling tower and is how most of the heat is carried away from the system. Based on just general thermodynamic properties of water, about 1.5 gallons of water are needed per hour for every ton of cooling. And this number is fixed. Since we want the cooling to occur, evaporation is generally not the focus of water efficiency. However, with that said, anything we can do to make the chiller plant more energy efficient will help lower your cooling load and thereby also reduce the amount of water needed for evaporation. So aspects of your facility that may impact your evaporative load include building design and envelope, HVAC design and equipment selection, lighting and plug loads, occupancy, operating characteristics, and maintenance practices. So lighting retrofits, system efficiency upgrades, and other efficiency projects that you implement that have energy savings likely will also have a commensurate water savings if you use a cooling tower. So beyond the water evaporated, some water can be lost due to drift or splash out. In a well-designed tower equipped with drift eliminators, this should be relatively minimal. However, if you're noticing visible droplets exiting your tower or ponding near your tower, this may require some attention in your facility. If necessary, drift eliminators can be added to existing towers, or higher efficiency drift eliminators can be installed to replace older, poor-performing ones. High efficiency drift eliminators also have ancillary benefits, such as helping to reduce the risk of Legionella. The other maintenance item to be aware of is cooling tower overflow. Many towers are equipped with an overflow drain to prevent overfilling the tower basin in the event of an equipment malfunction. If the level sensor or the fill valve in the tower fails, water then flows to the overflow drain and can kind of happen without facility staff really realizing it. So the photo on the slide is from a tower basin where the fill valve controlling the makeup was stuck partially open. Water was constantly flowing, overfilling the basin, and going down the drain. This is a good thing to try to check on daily rounds. Some newer systems also have BAS alarms that you can connect to your building automation system and can alert the operator to an overflow event. So, you know, if you get one of these alarms or if you hear water flowing down the drain when you're near your tower, this is definitely something you should remediate as water use from these overflow events can be significant. So to improve water efficiency of your cooling tower, the goal is really to concentrate minerals in the recirculating system. As the mineral concentration rises, the blowdown stream will bleed off a certain amount of water and replace it with city water, thus reducing the overall concentration of the minerals in the system. This measure of efficiency is called cycles of concentration. It's a measure of the concentration of minerals in the blowdown water to the concentration of minerals in the makeup water. It's also representative of the ratio of the makeup volume to the blowdown water. So the higher the cycles, the less blowdown you'll have occurring. If you recall our schematic from the cooling tower, the only water that's added to the system is makeup water. So when you're operating a properly if you're operating a cooling tower properly, the only significant ways water should leave is through evaporation and blowdown. Drift should be relatively negligible. So reducing cooling tower blowdown is the largest opportunity for water savings. The reason for the blowdown is to keep minerals or dissolved solids from building up in the tower and possibly causing issues like scale. As you can see in this example, city water contains dissolved solids. As water evaporates, these solids stay in circulation and begin to get more concentrated over time. If the concentration gets too high, the solids will begin to form scale on the surfaces of the chiller system, which can then degrade performance or damage the equipment. Therefore, some water is regularly discharged, and this is blowdown, and it's meant to keep the dissolved solids in check. This blowdown is typically controlled by a conductivity meter or controller, and careful blowdown control offers really the best opportunity for savings in the cooling tower system. So that background establishes the basis for saying that as you maximize your cycles of concentration and reduce blowdown, your system's efficiency will improve. To maintain high cycles of concentration, you'll want to keep minerals in solution by managing the system's water chemistry. Minerals are kept in solution by adding chemicals that can control the pH, inhibit scale, or inhibit corrosion. We encourage you to work with a water treatment vendor, and we have one as a case study today that shares your goals to achieve water efficiency. Working together, you can establish targets for your cycles of concentration based on your local water chemistry and water treatment options. I just mentioned that you should try to identify a target cycles of concentration that is achievable based on your facility's incoming water quality. This table is from ASHRAE 189.1, which is standard for the design of high-performing green buildings. ASHRAE establishes maximum values for certain parameters that recirculating cooling water should stay below. This information can be very helpful as you identify your cycles of concentration limit. So for example, if your limiting parameter is total dissolved solids, or TDS, you can identify your target cycles by evaluating incoming water quality. If incoming TDS is 1,000 ppm, for example, your tower may only be able to safely run at about 2 cycles because, 2,050 divided by 1,000 is approximately 2. If your incoming water has a TDS of 200, then you should be able to achieve a cycle of 10. So your treatment vendor should take regular samples of your incoming water quality and cooling tower water to help you identify your targets. And if they aren't providing this information, be sure to ask them to. In terms of retrofits to get the most efficiency from your tower, we've talked about some of these already, but install an automatic controller that operates the blowdown valve based on conductivity to allow yourself to maximize your cycles. Also install makeup and blowdown meters to track your water use on an ongoing basis. Monitor your trends and take corrective action if you need to. One important cost savings measure is that with appropriate meters, some utilities will let you deduct the quantity of water you evaporate from your sewer bill. These savings can be quite significant because cooling towers are big water users that evaporate a lot of water. So cost savings from a sewer deduction can be used to offset the upfront cost of installing meters and maybe purchasing other control mechanisms. Taking steps to improve your water quality, such as side stream filtration or basin cleaning to remove sediment, or even water softening if the incoming water hardness is a problem in your area, can also allow you to increase your cycles of concentration. Your water treatment vendor should be able to advise you on these options. And again, if they aren't offering these options, be sure to ask. This chart here shows the type of savings that you can achieve by increasing your cycles of concentration. So read the initial cycles on the left and across to the new cycles along the top. So for example, improving the cycles from 3 to 6 would provide a 20% reduction in your cooling tower water use. So you can see how significant the savings can be if you increase cycles. And this chart here shows water consumption for a 100-ton tower at various cycles of concentration. You can see from the shape that as you get higher cycles, there's a flattening of the curve that gets closer to that 1.5 gallons per hour value that I presented earlier. So if possible, you should try to achieve 6 cycles or greater to make sure you're optimizing your water use. This here is an excerpt from a pretty typical water treatment report. The format of these reports can differ, but the information is usually the same. So it includes conductivity of the makeup water. You can see that at the top there, 428. You also have the conductivity of the cooling tower water. This is the same as the blowdown water that gets blown down. So for this system, it's 2,755. Dividing the blowdown conductivity by the makeup conductivity gives you a little over 6 cycles. So in this case, it's not bad. One thing to also be aware of is where does your conductivity sit with respect to the control points. In this case, it's right at the upper limit, which is where you want to be. But if your conductivity of the cooling tower water is significantly lower than the set point, you might want to investigate a leak or some other problem that may be occurring. Another opportunity to reduce the amount of potable water that you're using in your cooling tower is to identify an alternative source of water that can be used to supplement or replace city water in the makeup line. Some possible sources include reclaimed wastewater, rainwater, foundation drain water, and air conditioner condensate. One thing you want to remember when assessing alternative water sources is that the water quality, quantity, and availability should all be considered. So only use alternative sources when you're able to match the quality of the alternative source to the need of the system. So for example, using blowdown water, it can be challenging because it's high in salts and chemicals, but something like air handler condensate is a great option for cooling towers, and I'll talk about that now. So yes, as I mentioned, AC condensate can be an excellent source of makeup water, particularly if your facility is in a hot, humid climate. Air handler condensate is water that forms on the cooling coils as it heats and conditions outside air. Condensate is typically drained to the sewer or sometimes the storm sewer, but since it is generated in highest quantities when the load of your cooling tower is at its greatest, it makes a really excellent source of cold, clean water to feed to your cooling tower. The biggest challenge with this type of reuse project is just the plumbing that's required to get the water from the air handlers to the cooling tower. However, if your pipe runs aren't too long or complicated, or if your air handlers are nearby the cooling tower basins, they can be very, very cost-effective projects. This is just some examples of some, albeit rudimentary projects that have been incorporated in some facilities that I'm familiar with. So they really don't need to be complex. It can be a little bit of pipe, some containers to collect the water, and a submergible pump to get it to the cooling tower basin. The Federal Energy Management Program, or FEMP, has created a really nice resource to help facility managers determine potential for condensate capture. As you can see on this map, facilities in the Southeast, Mid-Atlantic, and Midwest all have really high potential for these types of projects. That being said, cost-effective projects to collect and use condensate for cooling tower makeup can really be feasible in other regions as well, especially where air handlers are close to cooling towers. So certainly look into it regardless of where you're located. FEMP also has similar maps for rainwater and reclaimed wastewater availability, which are two other potential sources of cooling tower makeup water. And here's a few examples of some projects that have been implemented at facilities that I'm familiar with. As you can see, sometimes it's control improvement, sometimes it's AC condensate collection, sometimes just improving the blowdown controls. All of them you can find some pretty significant savings by paying attention to your tower and incorporating some of the best practices that I've talked about here. I'm now going to move on to boiler and steam systems. This will be the last mechanical system I'm going to focus on. There are really two main types of boilers. There's hot water boilers and there's steam boilers. Hot water boilers are either open systems that produce hot water for domestic consumption or laundry operations, or they can be recirculating closed systems that are typically used for space heating. Domestic hot water efficiency is mainly related to the efficiency of the water use. So installing high efficiency water labeled faucets, shower heads, laundry systems will help you save water and energy. Recirculating closed hot water systems are for space heating. You know, those should, similar to a chilled water system, they should have very little makeup water as well. So the focus of our presentation is really going to be on steam boilers. So this is a very simple boiler sketch to orient everyone again. Steam is produced in the boiler and used for space heating or potentially other uses. Once the steam gives up its heat, it condenses back to water and is often collected and returned to the boiler. This is the hot condensate. Similar to cooling towers, over time, minerals can build up in the boiler, and a periodic blowdown is required to remove them from the system. The blowdown is very hot, and frequently there's tempering water that is required to be mixed with the blowdown to help reduce the temperature below 140 degrees so that it is permitted to be discharged to the sewer. Makeup water is provided to make up for the steam losses and the boiler blowdown. The most important feature of an efficient steam boiler system is capturing steam condensate and returning it to the boiler. The water savings are threefold. Return of this high-quality hot water reduces water use and energy demand on the boiler system. It also eliminates the need for tempering water to cool the condensate before it is discharged. Lastly, it reduces the frequency of blowdown since the condensate is high-quality water with very low mineral concentration. Steam condensate recovery also results in energy saving. Since steam condensate is very hot, it just requires a lot less energy to reheat and produce steam all over again. Aside from installation of condensate recovery, the key to an efficient boiler operation is to really keep the components in good working order. So check your steam and water lines for leaks. Check to make sure that your steam traps are maintained and functioning properly. Regularly clean and inspect the boiler water and fire tubes for good heat transfer, and tune up your boiler for efficient firing, recommended on an annual basis. Make sure your steam lines and condensate return lines are properly insulated. That helps prevent heat loss. And one area that deserves maybe a little bit of careful attention and that might be looked at as you do kind of rounds within your facility is the tempering water application. So as I mentioned, tempering water is applied when hot water is discharged to the drain. This could be from boiler blowdown, flash tank, or condensate that's draining from the steam vents. These tempering water flows are frequently controlled by a temperature-actuated solenoid valve. If the temperature probe or the valve fails, tempering water can flow all the time, even if it's not needed. So as we saw earlier, these types of continuous water flows can be big water wasters, so that's something to try to pay attention to. Some other concepts that we presented earlier for cooling towers also apply to steam boilers. Install and read makeup and blowdown meters. Maximize the cycles of concentration by capturing as much steam condensate as possible and minimizing your blowdown. And again, work with a treatment vendor that specializes in water efficiency to maximize the cycles while still preventing scale and corrosion. This should reduce your water use, reduce your chemical use, and general overall operating costs. So I'm now going to hand it over to BK Ng, who's from Innovative Polymers. So I'll transition control, and he'll give a presentation for our case study today.
Okay, thank you very much, Robbie. Can everyone hear me?
Yes.
Yes, I can hear you, yes.
Good, okay. So today I'm BK Ng from Innovative Polymers in Singapore. All right, so we have 12 hours or 13 hours different. So I'm in the middle of the morning. Okay, so what I'm going to present to you today is about a green approach to cooling water management. So we have developed a system that is we call the Cal-Ion, or short form DCI, which is a chemical-free system for treating cooling tower water. Okay. All right. So my agenda will be, I'll introduce my company, and then share a bit about principle of cooling water management, which Robbie has covered very well. Okay, so I may run through that a little bit faster, and then I'll explain a little bit about our DCI technology, how it works, and then I'll share a success story that we have in Singapore here, and then share with you the benefits of having a DCI. Okay, so innovative polymers. So it's founded by myself and I have a partner here. Originally, we are a company that deals with engineering plastics. That's the reason why it's the innovative polymers. But both of us are chemical engineers by training. So we decided that we want to play our part in helping the global climate issues that is happening. So we decided to look at this area of cooling tower water treatment process. Okay. So for the principle of cooling, so just now Robbie has already explained very well. When you use evaporation to cool down the water, so whenever that takes place, the minerals in the water will concentrate up, and so this is where you get scaling and corrosion. And of course, when you recycle water, potentially you will have airborne bacteria, causing biofouling as well. So this is pretty standard things that happens in every cooling tower. Okay. So these are the three key problems that typically happens: scaling, corrosion, and biofouling. So scaling and biofouling will prevent or reduce your efficiency of your system. All right, so you ended up using more energy to generate the tonnage that you need. Okay, so the conventional methods, which was mentioned also by Robbie about chemical treatment, how you manage the conductivity, and then you do your blow down to try to reduce, ensure that the minerals in the water do not cross the solubility line. Once it crosses the solubility line, that's where you get scaling, and then of course you need to maintain certain pH to prevent corrosion, and then you have to add some chemicals to treat the bacteria to prevent them from biofouling, and of course the other kind of bacteria that they are most concerned about is the Legionella bacteria, which is can be quite deadly. Okay, so I'm going to explain about what DCI is. First of all, DCI we have patented it worldwide. It's a revolutionary approach to eliminate scale, and prevent corrosion and biofouling cooling system. So the objective, of course, is to save energy, water, and chemicals. Okay, and thus we are changing the way we treat water. Okay. I know there are non-chemical devices that has been introduced in the past, but I understand that it doesn't work too well, and there's quite a lot of skepticism on this part of it, but we have been very successful with our product. So hope that we can gain some traction here. So it was invented in Singapore. We patented it globally. We started marketing it in 2014. Now we have about 140 systems worldwide. So here we are not introducing some, great science. It's just electrochemistry that we learn in, maybe grade 10 or grade 12 kind of thing. Of course, coupled with our category, which is the anti-biotechnology and the intelligent software control that we have. So by doing so, we are able to manage the water very well. Okay, so what DCI does is that we dissolve existing scale from the pipes, cooling tower, the heat exchanger, and then on top of that, we prevent further scaling formation, okay, that are due to evaporation that happens continuously. So the way it happens, that we are able to dissolve existing scale is like this. On the right side here, we have here where my cursor is. This is where our electrode is. Okay. So what happens that we plate, using electrochemistry, we plate the scaling minerals onto our electrodes. Okay. So when we take the minerals out from the water that passes through our system, we deposit the scale in our system. So what happens then is that the water going back out to the cooling tower is very low in scaling minerals. But because it's very low in scaling minerals, then what it wants to do is want to dissolve scales that are already in the system, right? I think a simple common analogy that or everybody understands is probably this limestone cave. You have the stalactites and stalagmites. When fresh water, rainwater comes in, it's very low in minerals. You want to dissolve the scale, right? And then when it drops down to the bottom and the water evaporates, it forms back the scale. So here, the water going back to the cooling tower is very low in minerals, scaling minerals. So because of that, existing scale in the system will start to dissolve. Of course, it will take time because our system dissolves them molecule by molecule. Okay, so it takes time to, but eventually we will clean it up. Okay, the other part of it is that for cooling tower, the concern is corrosion. Okay, so for DCI, we actually consume the dissolved oxygen. So by lowering we lower the ORP. The reason we are able to consume the oxygen is because you use the oxygen for formation of your bicarbonates or carbonates, and also to generate the OH minus that to regulate the pH. So by reducing the oxygen, you definitely will help with reducing corrosion, and by maintaining a good level of pH. And we understand that at pH of somewhere between 6 to 8.8, 8.6 to 8.8, you form what we call passivated oxide. If you know chemistry very well, what you do is that you get Fe 402 or 403, okay, instead of the regular Fe2O3 oxide that you get, which is the normal rust that you get. So with the passivated oxide, it's a dark color and it doesn't fall off. That's how we prevent corrosion from taking place. Of course, the third area in terms of addressing the biocide is that with electrolyzing water, you actually also generate H2O2, hydrogen peroxide, which is also a biocide. And then, of course, if you have presence of fluoride in the water, you actually we will actually form chlorine out of that, which also helps to, as a biocide, treating the bacteria. Of course, what we are concerned about is the biomutation side, because we produce very consistent level of H2O2 and chloride and chlorine. So with our category, we actually are able to cause the bacteria to, in a sense, kill itself. It feels like it's not hungry and then it doesn't want to eat. So it die of starvation by itself. So by doing so, it doesn't have the propensity to want to biomutate because it just thinks that I am not hungry, I don't want to eat, so then it died, So there's no biomutation issues here. Okay, so we're able to handle the general heterotrophic bacteria and the Legionella bacteria very well with this category. So basically, this is a picture of our system. This is our controller area. This is the chamber with electrolysis chamber, and this is a category. So we have a small external pump that pumps the water through the system and then returns back to the cooling tower. Okay, so in the process of going through, we track the scales here, we sanitize the water here, and then once every hour or depending on your water quality in your location, we will do a regeneration of the electrode and then blow down through here. Okay, so our blow down water, of course, you can use it for other purposes, like watering plants and other things, because there's no chemical in there. So DCI separate hardness through electrochemical process. They concentrate scaling minerals are then blow down using minimal water. Okay, so during our regeneration process, we use very minimal water to flush out the scales. Okay. So since water quality is managed by DCI, the conductivity control blowdown no longer required. In fact, it's irrelevant for us because, the reason people use conductivity is that we are having the assumption that when the conductivity go up, your scaling minerals go up in tandem. But because DCI is removing scaling minerals selectively, so the other minerals and non-scaling minerals may contribute to the conductivity reading, but then it's not going to cause scaling for that reason. So DCI efficiently manage the cooling water with minimal water wastage. Okay. So this is a picture of the category. It's a proprietary device that we have invented here. Okay. So it's able to bring the material count within the WHO requirements, So with DCI plus category, we have a chemical-free approach for cooling water management. Oops. Okay, this is an example where we clamp a piping using gamma ray, and then after running for 2 months, the scales reduced from 14% to 2%. Okay, this one has a 21% scaling, and after 2 months, it drops down to 12%. So eventually, it will all go down to zero because, like I say, we dissolve the scale molecule by molecule. So it takes a bit of time to do that. Okay. All right. So this is we have only one size system. One unit of DCI can handle between 300 to 400 refrigeration tonnage, chiller capacity. So if you have bigger capacity, you just need to put in multiple units. Okay. There's pro and cons about having single unit and having multiple units. When you have multiple units, when one unit is down, the other two systems can help to manage it before you fix up the other one. If you have single unit is down, you got to get it done quickly. So this is a simple schematic of how our system works. When it's a standalone system, so when we are doing installation, we don't interfere with your system. You can continue to run your chiller system. We just pipe through from your infill in your cooling tower, draw the water through, and then push it through our system and return it back. Okay, so like I say, once every hour or so, we do a regeneration of the electrode where we blow down. Okay, so definitely, conductivity meter will no longer be needed. Okay, so I'm going to share some successful field implementation performance. Okay, so typically when we are installing in some place, everybody wants to know how you track the performance. So these are some of the parameters we look at. The chiller efficiency, if you have a BMS or EMS system in your facility, you can track the performance of your chillers. Okay. The other numbers are the condenser approach temperature, all right, which is your refrigeration temperature minus your water leaving temperature. Okay. So of course, if you don't have those things, we can always clamp your power line to look at your kilowatt usage. Okay. To establish the baseline. Of course, for the water side, we put a meter at the blowdown of before and after. So your conventional chemical methods where you have your blowdown, we put a meter there, water meter there, and then once we take a baseline, say over a month or 2 months or 3 months, then we will take that meter and install in our blowdown on our site so that you can track the the differences in the blowdown volume. Okay, so what we have here is in Singapore, the government is pushing very hard to to go green. Okay, so one of the objectives of Singapore here is that they want to achieve super low energy building. Okay, so this building, Keppel Bay Tower, it's already a platinum status building. Okay, so the current green building in Singapore, the highest grade you can get is actually platinum. Okay, you need to achieve at least, you must be able to run below 0.65 kilowatt per hour per refrigeration tonnage, and then you must have minimum 8 cycle of concentration. Right, that means you have to, your water have to be consumption has to be very, very good to meet that kind of standards. Okay, so what the government wanted to do is to go further than what the platinum standard is. So they're looking at trying to bring down the energy consumption by another 20% over the current best platinum standards. Okay, so we will pick as one of the systems to manage the cooling tower chiller system, okay, for this project. So here you can see that the baseline in November 2018, okay, the black line is here. So by January 2019, which is 2 months later, we already brought the efficiency down. Of course, in this kind of project, we must show the capability for at least a year or more. Okay, so by February 20th, we actually were able to bring down the performance even further. Okay. So here is a summary at the 70% load. Okay, the baseline they were running at 0.619 kilowatt. By January 19, we had brought it down to 0.584. So that's a 5.65% energy saving. By February 2020, we actually brought it down to 0.575. So we have a 7.1% energy saving. Okay. So the other part that we also save is that, like I mentioned, they were running at 8 COC, okay, 8 cycle of concentration. This is their blowdown, 7.2 meter cube. Of course, in our system, because conductivity is not relevant to us, what we do is we use the makeup water versus the blowdown water. So in their conductivity side, using conductivity, they recorded 8 cycles. Okay, but if you work the ratio of the makeup versus their blowdown, we still get 8 cycles as well. Okay, so using makeup water versus blowdown as a way to calculate COC is a correct method. Okay, because either way you get the same number. So with our site, our blowdown is 1.34 meter cube per day. All right, so we actually save 5.9 meter cube of blowdown that they have. That's equivalent to 81.4% water saving. So this is very significant. Okay, so we actually achieved 39.2 COC. Okay, so this is going to help a lot in terms of water saving side. Okay. So here is another summary of that water saving. Okay. Of course, you decide having energy efficiency and water saving, we still need to make sure that the water the quality of the water will still meet the standards that is required. So you can see that on the baseline, the numbers like hardness, they are 1.3 something. After we using our system, we are also able to manage the hardness within the range that will prevent scaling from taking place. All right. So you know, you will notice that the conductivity is higher, but then, like I said, we are running such high COC. Other minerals are contributing to this conductivity reading. So of course, the bacterial count as well, you know, we need to meet the standards as well. You say they were getting 4-digit count, we are getting 2- and 3-digit count, okay, for bacteria. So for Legionella bacteria, it's not detected, so we also show non-detection of Legionella bacteria. So, you know, so this is 7-8 months of data on the bacteria count, so that we make sure that we don't just like fulfill a short period of time. We have to ensure that we are able to meet all the requirements. You know, so with all the savings, energy saving, water saving, and chemical savings, we are still able to meet all the requirements. Okay, so of course the other one is about the corrosion. Okay, so you can see that on the mild steel and the copper coupons that we put in for 6 months, our mild steel corrosion is 1.18 mils per year, and copper is 0.03 mils per year. So this is well within the standards set by the Cooling Tower Institute in the US. They have this kind of standards that tell us. So we are able to control corrosion. You can see it on the mild steel here. Like I mentioned earlier on, you have this dark brown of almost black oxide. Okay, these are passivated oxide that does not come off, right? Okay, so we have many installations worldwide already. You know, these are some of the customers, you know, multinationals that uses our system. Okay, we have distributors around the world, so including in the US. Okay, so we are the Singapore Green Building certified product. Okay, our company has a ISO 9000 certified, and then our product is UL certified. Okay, the UL don't have operation here, so they uses TUV to do the testing for them in Singapore. So we submitted to them. So our product is UL certified, so it can be sold in the US without any issues. We are also CE certified that can be sold in the Europe without any issues. Okay. So the benefits of DCI, typically we get about 5 to 25% energy saving. Anytime greater than 50% water saving. Every time we double your COC, we actually give you 50% water saving. All right, and then if we quadruple that, we give you 75% water saving. Of course, chemical saving, you save 100%. There's no chemical required. Okay. If you are using for industrial application, you know, you will find that your process improvement is significant, you know, so your yield and quality goes up, your productivity goes up, right? Because you have less downtime. Many of our customers for commercial or industrial application, their savings are tremendous. Okay, so of course with all those kind of savings, you are reducing, you know, CO2 emission. Okay, so helping with the carbon footprint, you know. Of course, we are truly clean and green because there's no chemicals used. Okay. So thank you very much. This is the website for my distributor in the US, and these are the guys. You know, please write to them or download a questionnaire from our system, and then fill in the details and submit. Then they will be able to give you an analysis and a price quote on how much it costs and what is your ROI, return on investment through our system. All right, thank you very much. Over to Tara.
Thank you, VK. That was excellent results that you were able to get there. Thank you so much for explaining that all to us. So I have a few slides that are on some resources for WaterSense, but I'm going to skip forward so that we can get to our questions. We have a whole bunch of stuff on our website, best practices, guidebooks, checklists, worksheets, and other recorded webinars. Our newest one is our operation and maintenance checklist, which you can just print out and go around your facility looking for low or no cost changes that can save you water. So I'm going to skip forward. If you guys are interested, we have the registration links for the next webinars that are coming up. You can get this copy of the slides tomorrow, and you guys can use that, or you can use the training emails that come from Energy